Hello friends, welcome to our YouTube channel RF Design Basics. In today's lecture, we are going to study about the energy bands in semiconductor materials. We know all the materials in nature are made up of atoms, or we can say atoms are the fundamental building blocks of the materials. The atoms constitutes of positive nuclei which contains protons and neutrons. This nuclei is positively charged and this nuclei is surrounded by swarm of electrons or cloud of electrons. These electrons can have discrete energy levels. The distribution of the electrons surrounding this nucleus or distribution of the electrons in an atom decides the chemical property of the element, and this distribution of the electrons inside an atom can be represented by atomic configuration. This atomic configuration is a fundamental concept in physics and chemistry, explaining how the electrons are distributed in different energy levels and subcells around the nucleus. And the atomic configuration can be written as 1s2, 2s2, 2p6, 3s2, 3p6, like that. If you remember, we have studied this in our school. We can understand this atomic configuration with the help of quantum numbers. Quantum numbers are set of numbers that describe the property of electrons in atoms, including their energy, angular momentum and spin. We have 4 quantum numbers. First one is principal quantum number, second one is azimuth quantum number, third is magnetic quantum number, and fourth one is spin quantum number. The principal quantum number is denoted by n, azimuth quantum number is denoted by L, magnetic quantum number is ml, and spin quantum number is ms. These principal quantum numbers describe the energy level of the electron and its distance from the nucleus. It can be any positive integer like 1, 2, 3, 4, like that. Lower number indicates lower energy level and higher number indicates higher energy level. Here, higher the number, higher will be the energy level and higher will be the distance of electrons from the nucleus. For example, n is equals to 1 represents the first energy level, n is equals to 2 represents the second energy level, and so on. Second one is azimuth or angular momentum quantum number. This quantum number describes the shape of the electron's orbital and its angular momentum. So what are the orbitals? In an atom, orbitals are the region around the nucleus where probability of finding the electron is highest. This azimuthal quantum number can be any integer from 0 to n-1. If principal quantum number is n, then it will have value from 0 to n-1. For example, if n is equals to 3, then what will be the L? L will be 0, 1 and 2. Here 0 represents the s orbital, 1 represents the p orbital, 2 represents d orbital and 3 represents f orbital. This s orbital is spherical in shape, p orbital is dumbbell shape, d and f orbitals are complex in shape. Third one is magnetic quantum number. This magnetic quantum number describes the orientation of the electron's orbital in the space. What are the orbitals? S, P, D and F. So this quantum number will describe the orientation of the S, P, D and F orbitals. Magnetic quantum number can have value minus L to plus L. For example, if L is 0, then ml will be 0. If L is 1, then ml is minus 1, 0 and 1. If L is 2, then ml is -2, -1, 0, 1 and 2. That means this s orbital that belongs to L equals to 0, s orbital has only one orientation because it is spherical in shape. That p orbital corresponding to L equals to 1 will have three orientation. What are those three orientations? Px, py and pz. Similarly, this d orbital corresponding to L equals to 2 will have five orientations. It will have five orientations. So now we can say s orbital has single orientation because of a spherical shape in nature. P orbital has three orientations, px, py, pz, that is along x, y and z axis. D orbital will have five orientations, and F will have 7 orientations. This s orbital can hold up to 2 electrons. This p orbital can hold up to 6 electrons. This d orbital can hold up to 10 electrons, and f orbital can hold up to 14 electrons. Fourth one is spin quantum number. This quantum number describes the intrinsic angular momentum of the electron or the spin of the electron. It can only be plus half or minus half. Or we can say it spins up or down, and we can represent it by upward arrow and downward arrow. So after knowing about these quantum numbers, we can write the atomic configuration of any atoms. Now we will write the atomic configuration of silicon. So silicon has atomic number 14. So we can write it as 1s2, 2s2, 2p6, 3s2 and 3p2. So it has three energy cells, 1, 2 and 3. In first cell, this is s orbital. In second cell, s and p orbitals. And in third cell, s and p orbital. Here we have 4 electrons in the outermost cell. That is, these 4 electrons are valence electrons of the silicon atom. Similarly, we can write it for germanium also. Germanium atomic number is 32. So we can write it as 1s2, 2s2, 2p6, 3s2, 3p6. Here 4s2 and then 3d10 and 4p2. Why did I write this 4s before 3d? Because this 4s has lower energy than this 3d. And we know the above principle that says electrons will occupy the orbitals having lower energy first before they occupy orbitals which have higher energy. So this 3d has lower energy and 4p has higher energy level. In your school you must have studied this order of filling the electrons. I will go through it once. Suppose this is 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, like that. So electrons will fill this 1s first, then 2s, then 2p and then 3s. After that 3p and then 4s. Then 3d, 4p, 5s, 4d, 5p, 6s. So this is the order of filling the electrons in your cells and subcells. So this is also called Aufbau principle. Now let us concentrate on the energy level of the silicon atom. Suppose this is the nucleus of silicon atom. the far we go from the nucleus, energy is increased. Energy of the electrons will be increased. So ground energy level is the minimum energy level, that is 1s. Then 2s, 2p, then we have 3s and 3p. Suppose this is 1s orbital, 2s orbital, 2p will have px, py and pz. So px, py and pz. 3s, and again 3p will have px, py and pz. So now we will see the filling of the electrons here. So electrons will first go to the 1s, and this s orbital can hold up to 2 electrons. One will be upward spin and second will be downward spin. Why? Because of Pauli exclusion principle. Pauli's exclusion principle says maximum of 2 electrons having each opposite spin can fit in an orbital. So this must have the opposite spins, and this is called Pauli's exclusion principle. Similarly, 2s will have 2 electrons. This 2p will have 6 electrons. So again, this filling of the electrons, where the electrons go first, this is defined by Hund's rule. Hund's rule or Hund's rule. It says every orbital in a subcell is singly occupied by electron before a second electron is filled in this orbital. So it will be first singly occupied, and all these electrons will have same spin. Then the opposite spin electron will occupy. In same way, we will have 2 electrons here and 2 electrons here, 3p2. When these silicon atoms, this is for silicon, when these silicon atoms are in condition of bonding, this s and p orbital gets hybridized and form sp3 orbitals. Hybridized sp3 orbitals, and this sp3 orbital will have energy somewhere between 3s and 3p. This hybridization lowers the energy of the system and makes it more stable. It will have 4 orbitals, 4 sp3 orbitals, and each orbital has 1 electron. So these 4 electrons will act as valence electrons of the silicon. And these valence electrons will participate in bonding with the another silicon atoms. So this is sp3 hybridized orbital. These sp3 orbitals are tetrahedral in shape, and this will create a diamond structure when silicon atoms are bonded to create silicon material. We normally see the 2D representation of this bonding, where one silicon atom is bonded together with other 4 silicon atoms. One silicon atom will have 4 valence electrons. The other will also have 4 valence electrons, like that. This is only 2D representation. In actual, it has tetrahedral shape and it has diamond lattice. So this one silicon atom will have 4 valence electron and it will be shared with other 4 silicon atom. This bond is created by the sharing of electron. That is why these are covalent bonds. These are silicon atoms. And because of this tetrahedral structure of sp3 hybridized orbital of this silicon atom, the unit cell of this silicon material will have diamond cubic structure. Here, interatomic distance between two silicon atoms is 2.35 angstroms or 0.235 nanometer. So this is the required distance between the silicon atoms to create a bonding. And there will be approx 10 to the power 22 atoms per centimeter cube in a silicon material. So this is a very large number of atoms in a small volume of silicon material. Now we have seen here this silicon atom. When it is isolated, they have these energy levels 1s, 2s, 2p, 3s and 3p. But this is when they are isolated. What happens to these energy levels when large number of silicon atoms comes together to create bonding between them and create material? So we will see this in next lecture. Thank you.